So without any further ado, I will hand over to Harvey. And thank you, Harvey. We have your attention. Thank you.
Okay, thank you, Ernest. Okay, hopefully everybody can see the title slide. So, process safety time, SIF response specifications. If we consider the safety requirements specification for a SIF, or a pretty fundamental document, of course, perhaps the most fundamental document underpinning all that we do in functional safety, there are two key elements within that specification that we need to consider in terms of these timing issues. One is the trip point itself, which the SIF is invoked, and also, of course, the process safety time, the time available in which to suppress the hazard that is arising in the process. Those two fields within this specification are typically nominated by a process engineer. Now, the basis on which he might nominate those is a separate question, but typically it is within the domain of the process engineering, the chemical engineer department, to actually nominate both the trip point and the available safety time. It then falls typically to the C&I engineer to implement the SIF to meet those specifications of trip point and the safety time. And an important point here is that it is important for these two people to talk to one another. I have seen instances where the process engineer has dutifully nominated a trip point and a safety time, and the C&I department has gone on to try and fulfill that specification. And then they've realized that there's some difficulty with that, and so they've been obliged to procure an even bigger actuator to get bigger springs that will move the valves that much faster. And because of the additional weight, they've had to revise the support steel engineering. Whereas if they'd gone back to the process engineer and said, this safety time you've specified, how critical is that? They may well find that he said, oh, that's quite conservative, and you can quite easily knock 10 seconds, 30 seconds, whatever it might be, off that specification. So rather than just have them throw the specification over the fence, as it were, and leave the C&I engineer to cope, it's important that if there are challenges in implementing those requirements, that there should be that dialogue between the process engineering department and the C&I department to explore the significance of these specifications and what the possibilities might be, rather than to just unquestioningly implement the specification that's given. If we turn to the standard for a definition of process safety time, this is what we find: the period of time between a failure that has the potential to give rise to a hazardous event occurring in the equipment under control or equipment under control system, and the time by which action has to be completed in the EUC to prevent a hazardous event occurring. Sheesh, quite a difficult thing to get your head around. And technically a little suspect, in that the equipment under control, by definition, includes the control system. So the specification of EUC or EUC control system could be argued to be redundant. But there we are. That is the formal specification, but it doesn't really fulfill the requirements that we need in terms of specifying a SIF. Let me demonstrate that by turning to this plot, which shows a temperature rise in a temperature time plot, the temperature rise occurring in the process because of a cooling system failure. And we can see we've got the line here designating the trip setting, temperature trip point, and another line here representing the actual point at which the hazard would be realized, and we would suffer the consequences of whatever this hazard might be. And this particular trajectory just meets that hazard point. So we don't actually violate it. We don't actually incur the hazard, as shown here. And you can see another line here shows the point at which the trip action is complete, and because it's complete by this point, we just manage to avoid breaching the hazard point of the process. If that action was completed any later, then this trajectory would actually breach that hazard point. So in terms of the specification within the standard for process safety time, it's the time from the point of this failure occurring and the time by which we must complete the action in order to prevent the hazard. The difficulty with this is that this is indeterminate. We don't know what the nature of this failure might be, how severe it might be, and therefore what trajectory we might suffer when this incident arises. So this process safety time would vary depending on the nature of this initiating event, this failure. So not really satisfactory in terms of allowing us to identify what the response requirements are from the SIF itself. If we consider the time available from the declared trip point, there's the trip setting, and there's the action complete point, and again, we just avoid breaching the hazard point, this is the time that is available for us for the SIF to respond. It has to be faster than this time if we are to avoid breaching this hazard point. So in terms of the SIF, this is the available process safety time, which in this particular plot you can see is much smaller than the time from the initial failure. So that's a more appropriate specification for our purposes in defining the requirements for a SIF. And just to further illustrate that point, we show here normal operation and a failure occurring at this point, and we can see that it's over here that we actually breach the hazard point. So that's where we actually suffer the consequences. And with this particular example, we've got 100 seconds. But after that failure has occurred, it may be 30 seconds as shown here before we actually reach the trip point. So the available time for the SIF itself is only 70 seconds. And if the SIF responds within that 70 seconds, as shown here, 50 seconds, then all is good. But if this response time should exceed that 70 seconds, then the protection from the SIF will be illusory. It won't, in fact, give us the protection we need. So that's why this response time specification can be a critical concern. In many applications, there is no real difficulty in meeting the response requirements, but there are certainly those applications where it becomes a critical concern. So we do need to consider just what the points to consider are in defining this. So here is my revised definition of process safety time: the period of time between a SIF being invoked, in other words, the trip point, and the time by which the SIF action has to be complete in order to prevent the hazardous event occurring. Okay, and now I want to just explore in some more detail some of the considerations that would impact on this specification. So we may be clear on what the hazard point is within a process: the temperature, the pressure, the level, whatever it may be, the point at which we understand that the hazard will arise. But that specification in itself of the hazard point may be subject to a degree of uncertainty. If it's a bursting disk rupturing, say, there will be a tolerance on the specification of the burst pressure for that disk. If we specify a maximum level at which a vessel overflows, there may be some uncertainty in the precise level at which the overflow actually starts to happen. So because of that uncertainty in the hazard point specification, it is appropriate to back off from that hazard point by a corresponding degree to match that uncertainty and define a process limit. So to be absolutely sure that we will not breach the hazard point, we need to be confident that the process will stop rising towards that point at this process limit, which is distance from the actual defined hazard point by whatever tolerance we ascribe to the actual specification of that point, and indeed the process noise, because there may well be fluctuations in the process variable, whatever it is that we're concerned with, temperature, flow, pressure, etc. So this plot, which I'm going to continue to develop now through this presentation, shows this, what I've called here, a limiting case trajectory. So in order for the SIF to be successful and provide the protection we need, it mustn't breach that process limit if we are to be able to guarantee that we will not breach the specified hazard point. Another consideration here, this is that same limiting trajectory, as you can see here, that just meets the process limit. But once our trip action is complete, we've shut all the valves or stopped all the drives or whatever it may be, that doesn't mean that the process will immediately stop rising or falling if it's a low trip. And so there could well be a post-trip increment. So you can see on this plot, there's the horizontal line showing the latest acceptable time for trip action completion. So as long as we're complete by this point, we will just avoid breaching the process limit. But once you've shut all the valves, say, of feed lines into a vessel, and the concern is with an overflow, although the valves have shut, the lines could continue to drain into the vessel, and so the level would rise, continue to rise for a period after the trip action is complete. Similarly, if it's a temperature trip, high temperature trip, you may have switched off the heating, but it may be some time before the process variable actually turns around and starts to fall again. So there could well be this increment in the variable after the trip action is complete. And so we need to be aware of that consideration when we're specifying the requirements. Given that this, again, is the latest acceptable time for the completion of the trip action, and this is our trip setting, then it is from here to here that it constitutes the process safety time in accordance with our new definition. If the SIF is any slower than this, then this trajectory would in fact breach that process limit. And you can see we have, the other consideration is how fast this is moving. So the process safety time from those considerations is the process variable at the latest acceptable completion time minus the trip setting over the speed of approach. Now, there may be some difficulty in identifying what the approach speed would be. Typically, you would assume an average approach speed, but for some critical duties, then this might need some further consideration of the process dynamics and inertial effects within the process. But relatively obscure territory that, for the most practicable purposes, an assumption of an average approach speed will be perfectly acceptable. The actual trip point nomination, if it's a continuous variable, then of course the process safety time depends on the trip point. If it's a switch, if it's a level switch, say in a vessel, then the trip point corresponds with where you position the switch within the vessel. And so the same consideration applies to switches as well as continuous variables. How do we nominate this? Well, historically, this may well be, as I say, determined by the process engineers, and it may just be historical practice. It may just be a question of judgment based on experience. Implicit in that is the assumption of how fast the process is moving. If it is seen to be a critical concern for a given SIF, then it would of course be appropriate to undertake a more rigorous calculation of just what the available process safety time is. Another consideration is the tolerance in the trip point itself, because we can identify it as being at so many degrees or so many bar, but when we dial that into a trip amplifier or whatever it might be, or into our logic, there will be some uncertainty in that setting. So the setting of the trip amplifier will itself be subject to some uncertainty and could drift as well. And certainly that's true of the sensor as well, of course. The pressure transmitter, the temperature transmitter, or the switches, they will have an inherent uncertainty and accuracy specification, and also be susceptible to a degree of drift. So again, we need to consider these in our response time specification. And returning to our same process variable time plot, the same limiting case trajectory, you can see that we've specified here the trip setting, which is dialed into your trip amplifier, but the actual trip point could be delayed because of the offset due to the trip point error. And that offset will mean that there is a distinct delay before the trip is actually invoked. So we have to account for that as well. Just to explore the possible sort of significance of this, if we consider a pressure transmitter, 3051 will be known to many people. Reference accuracy for these transmitters is 0.04% of span. Or let me say, it was the last time I looked. Things may have changed. It's some time since I checked this. Total performance specification given as 0.12% of span. But if you are using a 3051 with a safety specification, then the accuracy is given as 2% of span. If we assume a 10 bar span for our transmitter and a 9 bar setting for the latest acceptable completion of the SIF action, and an 8 bar trip point, okay, nice easy numbers, and a 0.05 bar per second approach speed, then the implication is that we have a process safety time of 20 seconds. It would, at this speed, it would take 20 seconds to go from 8 bar to 9 bar. If our accuracy specification was the 2% we just discussed, that represents 0.2 bar. With that variable approach speed, that could give us a delay of 4 seconds. So although the process safety time was identified as 20 seconds, the maximum allowable SIF response time would be 16 seconds. So in some circumstances, this can be a key consideration. Very often not, but you can't always make that assumption. So here you can see the full diagram with all these considerations superimposed, the trip delay against the process safety time. Here is the SIF response time, so the time after the trip is actually invoked, so which may be a little later than the actual trip setting. And here we have the overall trip execution time from the nominated trip point through to the fully executed SIF. So the design requirement that flows from this specification of process safety time is that the SIF response time should not be greater than the process safety time minus the potential trip delay. And you will often hear talk of the specification, the SIF response time being 50% of this maximum. That's the often cited rule of thumb, but that can be questionable in many circumstances. The difficulty with that 50% rule of thumb is that it does not account for the potential growth or how fast the response time of the different subsystems within the SIF could grow, and it doesn't account for the mission time of the SIF. To illustrate the point, I'm hoping now to be able to switch to this software tool called SysSuite, which is a set of software tools for management of the functional safety lifecycle. There are a variety of tools here: HAZOP, LOPA, SIL compliance, but the one I'm concerned with is process safety time. And if I open this record, hopefully everybody can see this. We've tried to size this so that it will be readable on people's screens. I hope you find that's the case.
Thank you.
Okay, so here's a notional level trip. You can see the corresponding process data here. It's a high trip. The hazard point is set at 10 meters. These numbers are all invented, by the way. This isn't a specific application. This is teed up just to be able to demonstrate some of the considerations to you. So hazard point 10 meters, a 0.1 tolerance declared for that, a 0.1 meter post-trip increment, 0.01 meter noise amplitude, and from those specifications, we calculate the process limit is 9.795 meters. We've specified an approach speed here, and we've nominated the trip setting at 9.2 meters. From that, we calculate the process safety time of 14.9 seconds. Okay, that's the process specification. Then on the right here, we have the corresponding SIF instrument data. And for each subsystem here, sensor, logic, final element, we declare what the response time is when newly installed. Okay, 3 seconds for the sensor subsystem, 1 second for the logic subsystem, 5 seconds for the final element. That gives us an overall SIF response time of 9 seconds, which is found to be valid. That's the maximum allowed SIF response time, 14.65 seconds, which is a little bit less than the process safety time because of the trip point tolerance, okay, which would potentially delay the start of the SIF response by up to 0.25 seconds with the values that I've entered here. And you can see that that's valid, but as a percentage of the process safety time, it's greater than 50%. It's at 62% of that value. So in accordance with our rule of thumb, this would breach that requirement. Here I've specified the mission time for the subsystems, all declared to be 10 years, and have identified growth rates for each of these subsystems. And we can also specify whether that growth characteristic is linear with time or exponential. And in this particular example, I've used 7% exponential for the final element. 7% exponential across 10 years represents a doubling of the response time in that period. So this is equivalent to the 50% rule of thumb. The 50% rule of thumb is essentially saying you could, the SIF response time should be able to double and still meet the requirement. So in terms of an exponential characteristic, 7% a year across 10 years would represent that doubling, as you can see there. So here we've calculated the response time after the mission time has elapsed. And you can see that at 15.7 seconds, this is too slow. This would not meet our requirement. But this is where we can start to edit the requirement. So I'm not going to change the process specifications for the moment, but what we might do, for instance, if this is a valve, we might say that we allocate a mission time of 5 years for the valve, so that after the 5 years it will be overhauled and returned to the as new condition. And you can see that change there. And although this measure here doesn't change, of course, so we're still at 62%, we're still breaching the rule of thumb. But because we've now detailed the mission times and the growth characteristics, we can see that, in fact, this would be a satisfactory design. So whereas here you might be prompted to go away and specify a different valve, different actuator, in fact, it might be perfectly satisfactory given our specification for growth rate and mission time. Imagine this was a not a valve, but a contactor. We're opening a contactor to stop a drive, and then it might only be 1 second is the expectation when new, but we might now have a mission time of 30 years for this contactor or breaker. For such a piece of equipment, I would expect a very low growth rate. I'm going to say 0.5%, and I'm going to say linear. You can see this is on the rule of thumb basis, we're still handsomely below the 50%, and even after the mission time has elapsed for each subsystem, we still have a SIF that will meet the requirement. But on this level application, somebody might say, I don't know why this trip setting is so low. We could get more into that vessel. We're being too conservative here. So I might come to the process specifications, and let's make that 9.4 meters now. So we squeeze some more into this vessel. We change nothing else. Okay. We've now breached the 50% just marginally, but this tells us we're still good. Right. Make that 9.5. This again now tells us that we're well beyond the 50%. So you might hesitate at that point. But in fact, given our declarations about mission time and growth rate, then response time after mission time has elapsed is still satisfactory. So this may be a perfectly satisfactory design proposal. So you can see there are quite a few. Consider I could keep pushing this, but obviously at some point it will become a problem. So now we're in all sorts of trouble now. Far too high. Six. Over 100%. Still too slow here. Okay, as we were. So typically, if it's an electrical final element, if it is a contactor or breaker, then usually there wouldn't be any real difficulty in meeting the requirements. But depending on the process specification and how close to the wind you want to sail in terms of the trip setting, it could be a concern. Obviously, I've demonstrated all of this just by considering the final element response time. Logic, typically not a concern. Sensor response time could be an issue, particularly if the process is subject to fouling, coating, developing on sensors, thermal wells, etc. Big valves, of course, if they're suffering fouling or the seals are beginning to degrade, could introduce stiction into the valve travel, could, of course, cause some growth there. Okay, you should be seeing the presentation again. There is our specification of the design requirement. And here are some suggested values for growth. So for the electrical type system, a nominal 0.5% per year, I'm suggesting as a suitable value. So this is where there's no expectation of significant growth. If the duty is clean, non-fouling, a relatively benign duty, then we might nominate a very low figure, 0.5%. If it's a relatively clean duty, so significant growth not expected from fouling effects, but there could be stem, steel, frictional effects, etc., a nominal 2%. If there is potential for growth through dropout, deposition, biological growth, etc., then the suggestion here is they use the 7% exponential or 10% linear, which equate to the 50% rule of thumb. It allows a potential doubling in the response time before the specification will be breached. There we are, everyone. That's hopefully been of interest. If your interest is piqued, you can learn more about the Institute of Measurement and Control, of course, at the website, and indeed the Functional Safety Special Interest Group. That's my book that some of you may already be aware of. And if you have any interest in the software that I just used to demonstrate the response time specifications, you can visit the syssuite.com website for further information there.